Hello and welcome to Pre-Calculus Honors, Chapter 3, Section 1, Part 2, or Part B, Exponential, and today we're going to focus on logistic functions, right? So in class we talked about exponential functions. Today we're going to look at logistic functions, which basically come in one of two forms. Either you're going to have some constant divided by 1 plus some constant times a base to the x, where if you have an arbitrary base, that base b had better be less than 1. So this base is going to be a fraction or a decimal, less than 1, right? Where a is going to be a positive real number, c is going to be a positive real number, right? So if you see something of this form, that's a logistic growth function. Or more commonly seen would be, again, a positive constant up top divided by 1 plus a positive constant times e to the negative kx, where k is a positive number, so you do have a proper e to the negative something x, right? If we let c and a and k all be 1, we get the basic logistic function, 1 over 1 plus e to the negative x. This was one of our 12 basic functions that we covered earlier at the beginning of the year. So let's just review what the basic logistic function looked like again, right? It looks like this. If you graph this, we can see its domain is all real numbers. Its range, however, is between 0 and 1, not including 1 and 0, right? We've got our horizontal asymptote above and horizontal asymptote below. There's no x-intercept because, again, my range is y is strictly between 0 and 1. The y-intercept is right here at a half, and that point is also sometimes called the point of symmetry. It's called the point of symmetry because if I were to take this graph and spin it 180 degrees, I get the exact same graph, right? So the logistic function is symmetric about this point of symmetry, right? An odd function is symmetric about the origin. You can spin it at 180 degrees. The logistic function is symmetric about this point of symmetry, which also happens to be its inflection point. This is the point where you change concavity. So here to the left, right? So for x less than 0, I'm concave up. But for x greater than 0, here I'm concave down, right? So this is also an inflection point. The horizontal asymptotes are 1 and 0. It's bounded above and below by 1 and 0. The right end behavior, left end behavior, it's 1 to 1, concave up, concave down, right? So go ahead, pull out your calculators, and let's practice graphing some logistic functions. So 4 over 1 plus 2 times 0.4 to the x. Again, this is a logistic function because my base here is less than 1. And I've got a constant over 1 plus coefficient base less than 1, x. So when you punch that into your calculator, right, go ahead and change the view. How do you know what the view should be? Well, the x's typically don't have to be that far apart from each other. How are you going to know what your y value should be? This constant up top, right, is going to be kind of like your upper bound. And then if this is a proper logistic function, your lower bound should be 0. So if you graph over -5 to 6, 0 to 4, you're going to get a good picture of your graph. And what's the y-intercept? Well, if you plug 0 in to your exponent here, you're just going to get 1. So this is 4 divided by 1 plus 2, or 4/3. And we can kind of see that right there. 4/3, so 1 1/3 more. And the asymptotes are at 0 and 4. So the symmetric point, which is also the point of inflection, you can find by using your calculator to find the inflection point, right? And so what you'll notice is this is always, the y value of this is always smack dab halfway between your two y horizontal asymptotes. So go ahead, you try right now. Grab your calculator, graph f of x equals 10 divided by 1 plus 4 times e to the negative 2x. And from that graph, tell me what its asymptotes are, find the y-intercept, and also find the point of inflection. So I'm going to pause the video. I'm going to grab my calculator. You do the same. Pause and graph this on your own. All right, if you're having any trouble graphing it, be sure you don't type the letter E, but you go to this pi symbol and choose E for e to the negative 2x. And lo and behold, that kind of looks like an exponential function, right? And all logistic functions start out looking like that. What's my coefficient up top? 10. So how about I change my view? let's go zoom, settings. Let's let our y values be from, instead of negative 6.0 up to, I'm going to guess 10, because that's what our coefficient up at the top is. And if we just hit OK, lo and behold, there you have it, right? We don't need to go from negative 10 to 10. So let's zoom in just a little bit more. How about, let's go, negative 5 to 6 again. Maybe that'll also be good. Yeah, and we can kind of see it's shifted over a little bit. So my point of inflection is going to be right around here. What would the y value be for your point of inflection? It's going to be halfway between 0 and 10, so it's going to be 5. How do we find it? Go to Menu, go to Analyze Graph, Inflection. Again, your point of inflection, just below and above, boom, it's right there. 0.693. And again, the y value is 5. So what do we see? Oh, I forgot to figure out what the y-intercept is. Well, so y-intercept, we can do that directly by plugging it in, right? F of 0 is going to equal 10 divided by 1 plus 4 e to the 0. Well, that's just 1 plus 4, so this is 10 over 1 plus 4 is 5, 2. So my y-intercept is going to be at 0, 2. And that sure looks like 0, 2 to me, right? This is 5. Good? All right, so your two asymptotes are 0 and 10. The symmetric point, right? It's always going to be between your two asymptotes, between your upper and your lower bound. So the graph of a logistic function at first appears exponential, right? What we saw before we zoomed in is that at first looks like it's an exponential, but then eventually it caps off and it's bounded above. So logistic growth can model spreading diseases, rumors, and long-term population growth. So let's look at a couple examples of that now. So what we've got here is the census data in millions for Illinois from 1900 to 1990 is given below. So this is 1900. There were 4.8 million people in Illinois versus in 1990, there were 11.4 million people in Illinois. So find the logistic regression model for the population. So first things first, put the year and the population data into two lists in your calculator. So go ahead and do that right now. I'm going to pause so you don't have to watch me type it in and get there. So pause the video. Alrighty, so here's my list of years and my list of population. So to get that logistic regression model, first let's get a scatter plot of this data. So I'm going to add from data and statistics, right? Click to add a variable. So I want the year for my x-axis and the population for my y. And we can kind of see this. So to get the regression model, we're going to go to Analyze, Regression. And we want the first logistic where d equals 0. I'm not going to go into y, but it's this first one, show logistic. And thus we have a logistic model. So go ahead and copy this equation down, right, off to the side, and we're going to store that in a function. So I'm going to go ahead and go to a new graph here, and I'm going to go ahead and type that in. You'll see I rounded the numerator, right? So 14 divided by parentheses 1. What am I typing? 1 plus 1.953, again, times E. Be sure you're using E to the negative 0.02573x. All right, so now again, in standard view, that does not look very helpful. So we want to make our scale. Again, we were specifically looking at the data from 1990. So we were looking at 0 to 90, right? But if we wanted to even go back before then, right, what would negative 90 look like? And for your y scale, again, we don't need a negative value. And up at the top, it looked like we had 14, right? So there we've got more of our logistic model. And If we graph over -150 to 200, we can see an even better, more complete picture. So let's go to -150 to 200. And that, there you go, definitely looks a whole lot more like our logistic model. So, write a logistic regression model for the population. We get that equation from our calculator. Graph the function and predict the population in 2050. All right, so to predict the population in 2050, let's think a couple things. So first, 2050, if I subtract 1900, right, because that's when x equals 0. So in this case, x is going to be 150. So I want to plug 150 into my function. Since this, on my equation, it's f2. So if I go to calculator, I can just do f2 of 150. And it will give me 13.4465. Again, because I rounded and I didn't copy the exact equation this time, but about 13.4 million, right? 13.4 million people, according to this model, is what we would predict. So determine the maximum sustainable population or carrying capacity. Again, what was my upper bound? According to this model, the population will level off at about 14 million. And that's where we're going to end this first video, because this next example is going to take a little bit more than what my recording will allow me to fill. So end video 1 and start video 2 now, please.